All right, class. This is a tension pulley problem. There's your pulley, okay? And you've got two blocks. One block is 3 kilograms, 5 kilograms the other block. Now, which direction do you think this will go? Yeah, this will go in the direction of the 5 kilograms, okay? Do you know what the easiest way to do a pulley problem is? No, I didn't say the easiest way to not do it. I said the easiest way to do a pulley problem is to draw a picture, and we are going to change the pulley into one of these pictures on the board. Which one shall we change it to? Which people? The tug of war? The tug of war. Exactly. You're going to straighten out the pulley, and you're going to change this into a tug of war between two blocks. Exactly right. So, you have your 3 kilogram block, and you have your rope, and you just pretend the pulley's not there. No, it says frictionless in the problem. It's frictionless rope. Frictionless rope. So we have a tug of war between two blocks, Greenie. Alrighty. Now, that is the 5 kilogram block. We'll call that negative gravity B. But this one is pulling opposite of the blue block. The 3 kilogram block is opposite, is it not? Yes? Okay. So that would be what? Considered positive gravity A. All right. The thing isn't going anywhere, or if it were tug of war, okay. Well, we need to find that it's going to go somewhere, right? Because obviously the 5 kilograms mass is going to win. So is this going to have a net force and a net acceleration, Chase? Point which direction you think this will have a net acceleration. Yeah. Okay, so if it moves right, that means we definitely had a net force, did we not? Okay, so what would the net force of this thing be composed of? Well, it would be composed of the weight of A and the weight of B. But the weight of B is opposite that, so it's negative. Right? Everybody understand what we did? Somebody explain it back to me. Somebody smart. Christopher, explain back to me what we did. We took the pulley problem and we made it into a tug of war. And then why are we using F of G twice? Well, they try to cancel each other out, but one's going to win, isn't it? Okay, so this heavier block's going to win, correct? So then if these things move, do we have a net force? We've got to. In order to have any acceleration, you've got to have a net force, right? Right, Allie? You good with this so far? Christian? Peg and Param? You guys good? All right. Do we know what the net force is yet or no? We don't. But can we find these guys? Can we find these weights? We can. How? Both of them are being affected by what? Gravity. So, 3.0 kilograms. Okay. Now again, what did we just say this was? Because it's a tug of war. We treated it like a tug of war. So that means one's got to be in a negative direction and one's got to be in a positive direction. So that means for this one, we got to make gravity positive. Al, explain to me why we just made gravity positive. Because it's acting which way? Opposite of this one. Okay? This one we're going to keep gravity negative. So minus 5.0 kilograms times 9.8 meters per second squared. Or if you like, I can do this. Plus negative 9.8 meters per second squared. How's that, Logan? You like that better? All right, sorry about that. Right now, I want you to add up the net force for me, please. F net. What do you get, Christian Lasher? What'd you get, Ariana? Shrug shoulders? You got shrug shoulders. You got negative 19.6 as your what force now? What did we just find? We just found the net force. We just found the net force. Okay. Uh, wow, that's a great job there, Christian Lasher. That's fantastic. If our net force is negative 19.6, then Jacob Ross Spencer is the whole thing, both blocks, going to move that way. Y'all ever played tug of war? Does one person stay here and then the other person, or do they both move? Yes. So if they're both moving this way, do we combine the masses? Is the whole system moving? Does that include both masses? So we have a net force with both masses. So if we have a net force, is negative 19.6 newtons, then shouldn't we include both masses in our mass to find the acceleration? Shouldn't we do that? Find the acceleration. You said how, Ariana? You said wow. Good. Negative 2.45 meters per second is my acceleration. Christopher, is that what you got? Okay, so this whole system is going to accelerate up or accelerate down. This side, what's this side going to do? The right side. It's going to accelerate, well, the right side over here, this side of the pulley, is going to accelerate what? Down at negative 2.45 meters per second squared. But then this side of the pulley is going to go up at what? Positive 2.45 meters per second squared. One side goes down, one side goes up, right, Christian? If it goes like this, isn't that the same as a tug of war going that way? Jacob, you don't like that, man? What don't you like about it? Ross, okay? Spencer, it's all right? Indigo, you don't like it at all. Indigo, you don't like school. You liked school last year. You were a super overachiever. Terrence likes school. Okay, so that is a one pulley problem. That is how you do a one pulley problem. No, we're not doing two pulley. Well, we'll get into, I'll tell you what, what's tomorrow, Friday? We'll do a two pulley problem tomorrow, but we're not doing it right now. Because right now I'm just trying to get you guys to understand net force. No, honey, I'm not going to put a two pulley problem on the quiz. Just one pulley. Well, we'll get into it later. Kill you. He killed the kid. So, if we look at problem number 76, okay, I'm going to let you guys do 76, but if we just look at it for a second, Logan, if you guys look at problem number 76, is that basically similar to what we just did? Yes? Flip the page back. Look at my picture here, problem number 76. Okay? So, yeah. Now, I want you guys to do this. All you got to do is find the acceleration of the question mark there. Okay? Now, think about this. The whole system, okay, the whole system, it says a resistance-free surface, and it's on ice. So if they're having a tug of war on ice, what would happen to them? Both of them would, right? Now, would both of them move this way or move that way? Or would they go and come together? They're going to move together. So the whole system, Allie, is not going this way or that way. So if the whole system is not going this way The whole system is not accelerating this way. What's the net force on the whole thing? You don't get it, do you? Okay, here we go. All right, so uh, they're pulling on ice. The key is the pulling on ice, right? So this girl is going to go this way. Crap. This girl is going to go this way, and this boy is also going to go this way, right? Maybe not as much, but if you treated them as one big system, are they both going this way? No, they are not. Are they both going this way? No, they are not. The overall movement of both of them together is what? What is the overall acceleration of both of them together? All right, let's look at this another way, Allie. Allie and Hannah Rapp are on roller skates. Here we go. Here's Allie. She's on some roller skates. There she goes, roller skates. Okay, is she shorter than you? Yeah? Okay, there we go. Okay. All right. She's shorter than you by a little bit. No arms. Okay, they got... Okay. They're tug-of-warring each other. They're tug-of-warring each other. Where are they going to go? Okay, they're going to go this way and this way, right? Okay, if we look at the Rapp sisters, where did the Rapp sisters go? Where did they displace? 0. They both moved. They're both on roller skates, right? Okay, great. Where was the overall net motion of both of the sisters? Did they both move a direction at the same... Did they both move the same direction? No, they didn't. They moved opposite each other. Did they both end up in a different spot? In other words, did the Rapp sisters both move over here? Did the sisters move over here? No. Did the sisters move that way? Did both sisters move that way? Then what was the overall acceleration of the sisters? Nothing. So what was the overall net force of the sisters? 0. If there was a net force in this direction by both of the sisters, then both of the sisters would have ended up over here after their tug of war. If there was a net force this way, both of the sisters, the Rapp sisters, would have ended up on that side. Over here. You guys have played real tug of war before, have you not? Okay, when you play real tug of war in the gym, do both teams go right there in the middle? No, what happened? This team is stronger than this team, and they pull this team across the line, but this team moves over here, and so does this. So both of the teams moved over there. Was that a net acceleration? Was that a net force that way? If both teams went into a pile, where did the middle move? That's basically what I'm saying. All right, let's look at this one more way. Okay, right here, you guys have played tug of war with the flag, right? The flag is on the rope. Okay, let's think of it that way. Here we go, Rapp sisters again. Rapp sisters. Okay, there's Allie. Okay, there she is. She's got the roller skates. Okay, here's Hannah. She's down here. Okay, and in between right here, in between this rope, you have a red flag. There's the red flag. Okay? You got me? You both pulled each other in, and you went splat. Where'd the red flag go? Nowhere. So if the red flag didn't end up moving, it didn't end up going that way, and the red flag didn't go that way, where was the overall net acceleration? 0. But now if you're not on roller skates, you take the roller skates away and you put shoes on. It's a different story, isn't it? Now it's a much different story. Now where does that red flag get moved to? It gets moved over here. Yeah? Is that a net acceleration? Yes. Is that a net force? Yes. Sleep, Christian? Okay, so now I want you to do number 76 with that in mind. Ready? Draw picture, go.